One, two, three, testing. One, two, three, testing. Can you hear me?
Well, right at that time, of course, we have a student that wants to test their Zoom. Yes, we can hear you loud and clear. Go ahead and please mute yourself. Oh, perfect. Hi. This is a Wednesday night amateur radio class, a beginning amateur radio class. The technician level is the beginning level in the United States. Then there's general class and amateur extra, and we teach all of them. I'm your instructor tonight, Gary, ham radio call sign Whiskey 4 Echo Echo Yankee, and we're working out of this book right here. It's the Amateur Ham Radio License Manual from the ARRL, the 5th edition with the red cover, and this is the book that we work out of, and we go chapter by chapter each week. And the whole point is to get you prepared to take a 35-question multiple choice test and get your ham radio license and get on the air. Tonight we're going to be into chapter 4 in the book, Propagation, Antennas, and Feed Lines. But before we jump into that, I just have a little kind of a general thing that you may find interesting. If not, you just leave it. But taking multiple choice tests. Bruce, if you'd go to the laptop, I wanted to point out how the tests are typically constructed. And I just found this generic thing online. Let me turn on my laser pointer. There we go. So you've got, they call it a stem, but you've got your question, the question that you're going to be answering. And then you've got down below the various answers that you could have. Note distractors. In this case, they have 3 distractors, which are not the right answer. If you look at our tests, typically there are 2 distractors that can't possibly be the right answer. And so then you're left with 2 that could be the right answer. And so that might help you if you get stuck when you're taking your test. Find the distractors first. No, oh, that can't be true. Well, that can't be true. And see what you're left with, and then see if you can find the best the answer for that. So, all right, that was just a little something I thought maybe you'd be interested in, because we're getting closer and closer to test-taking time. So tonight, Chapter 4, Section 4.1 is called Propagation. And one of the most common questions I'm asked is, well, how far does a radio transmit? And the answer is always, well, it depends. And that's what we're going to talk about tonight. So radio waves, just kind of a review, are electromagnetic waves. And the range that these electromagnetic waves can dissipate and be received, that's called the range. It's the distance over which a radio transmission can be received. And the radio horizon, that's the distance over which 2 stations could communicate by a direct path. So when you get your technician license, you'll have your first radio is probably going to be an HT, a handy talkie. Well, how far can that go? So if we look at 6-foot people, let's say, they're holding their radio up high, because of the curvature of the Earth, the horizon, the radio horizon, is going to be out about 3.5 miles. Got another 6-foot person on the other side. He's got, or she got 3.47 miles as well. So theoretically, if you didn't have trees or buildings or obstructions in the way, about 7 miles if you're on the ground. Now things change, however, if you can get one of you up high, or if you have a tall tower, or if you're working through a radio repeater that has a tall tower. So we'll talk more about that. But the common question, and if you see the ads, oh, this radio goes 20 miles. Well, maybe under the right conditions. Propagation, the way that radio waves leave the antenna, there are 3 modes, or space wave, also known as the direct wave. That's from one antenna direct to another, point to point, we might say. There's something called ground wave, which happens with medium wave signals, where the radio signal follows the curvature of the Earth. And then sky wave, which is when you have a signal that goes from an antenna up to the ionosphere or troposphere and is refracted or bent back down. So let's talk about that direct path space wave. That's a line of sight. And as I mentioned, obstructions can limit the distance. So in this case, we have a short tower here, or there's a hill or a mountain in the way. It can't be received over here, and this because it's being blocked. This is VHF and above is line of sight using this direct path. Now, if you can get the taller tower up, well, you can go over the obstruction and make it and be received at the far end. So things you want to keep in mind. The radio horizon, that's the direct path communications. One thing to know that the Earth actually bends radio waves slightly. So where the blue line you see here, it would be for like a laser or a light beam that goes off into space. Because of the refraction toward the Earth, the radio horizon for radio waves is a little bit farther, about 15% than it would be if it was just strictly a line of sight. You got an obstruction? Does it have a sharp edge? There's something called knife edge diffraction. If you can direct your radio signal toward a sharp point, the radio waves can be refracted around that, and you can get signals around barriers. So that's one mode of propagation. The thing is, there's never just one mode of propagation. There's always various ways that radio waves are getting from point A to point B. So let's take this case here. We have our transmitting antenna here. We have the direct path here, and so it's going to our little radio over here and being received. There is some attenuation because of the trees, the foliage, the leaves and whatnot. So there is path loss here. Another way that the signal might be coming to our little radio there is through reflection. The radio wave comes from the antenna, is reflected off of a flat surface on a building here, and it comes into the radio. Another, we talked about knife edge diffraction. If it comes in here and there's a sharp edge, it can be diffracted around that and into the radio. The point I want to make here about the various paths the radio waves are coming in is that sometimes they can be additive and make the signal stronger. Sometimes they can come in out of phase and they can be subtractive and can make the signal go away. We're going to talk more about that here in just a sec. All right, this is my story about trying to receive WSPA TV at a QTH I had in Greenville, South Carolina. I was on one side of a small mountain called Paris Mountain, and WSPA, the TV station, which was on a VHF frequency, was on the other side. And so the direct path from WSPA's transmitter wouldn't make it through Paris Mountain to my house. But knowing what we just talked about there, I did have a directional TV antenna on my roof. I was able to take that antenna and turn it pointing toward downtown Greenville, where they have large buildings. And I was able to find a reflection path, and it allowed me to watch WSPA TV, when otherwise I could not, all because of this propagation mode, reflection. That's the VHF and above. You can do this sort of a thing. So I mentioned that when signals combine, they can add or they can subtract. Have you ever been in your car, listening to your favorite FM radio station? FM is a VHF frequency, the 89 to 107 megahertz. That's VHF. And you've got various signals coming into your car, and you have to stop for a stoplight. And you're coming up to the stoplight, and you get stopped. And then your favorite music was on, and all of a sudden it went away. What happened? And then you discover that if you creep the car up maybe just a foot or 2 feet, all of a sudden the signal comes back. That's multipath. You're experiencing more than one signal reception path coming to your car antenna in this case, and it's being instead of being additive, it's being subtractive and taking away the signal, and that's why it went away. But if you move just slightly, you change the equation, you change the signal strengths, and you get your signal back. So if you've ever wondered why does that happen, that's it. Multipath. And multipath can occur on all frequencies, of course VHF and UHF, but also on medium frequencies and high frequencies. You might remember listening to or watching an old World War II movie, and the people are listening to international shortwave, and the signal is going up and then down and then up in strength, and you kind of hear the fading and you have to listen harder. That's multipath. That's multipath from signals coming from the ionosphere. In your home, when you get your license and you get your HT and you want to log into the local repeater, you will find there are spots in your home that are better than others. You'll find that maybe if you stand maybe 3 feet away from a window or whatnot, you can hear the radio repeater just great. You can hear what's going on. But if you move over just a few feet, all of a sudden the signal goes way down. We say that when you find your sweet spot, that's your X. And you'll sometimes hear people on repeaters, if you're moving around, not thinking about it, somebody will yell, "Hey, you're off your X. I didn't get any of that conversation. You faded out." Because multipath happens not only on reception, but it also happens on transmission as well. So your signal might be lost getting in to the radio repeater. So the little handy talkies, I have one over there, I forgot to grab it. They're FM radios. They transmit a frequency modulated signal. And back in the day when, before the internet, hams were interested in computers and bulletin board systems and dial-up modems, but rather than tie up the phone line, well, why can't we do this by radio? And so packet radio was born. It predates the internet, and you used a computer or a terminal node controller, a TNC, and a radio. And the computer would be running a special program to communicate with the TNC. The TNC would take that and code it into audio tones and send those audio tones plus a push-to-talk signal to the radio, and you would send and receive packet radio. This is an early form of digital communications. Now, digital communications are great, but they are not immune to multipath. With digital signals such as packet radio, if you get multipath, what happens is the error rate for the digital transmission goes up, and your throughput, the amount of data that you can transmit, goes down. So just know that the digital signals can be affected by multipath, and when that happens, the error rate goes up. And here's a little pictorial of, again, a packet radio station. Packet radio still exists today, although not as popular as it once was. But if you've heard of APRS, and that system allows you to send your location, latitude and longitude, and other information, that is an outgrowth of packet radio. So we saw in that earlier diagram a tree that was kind of blocking a path and attenuating a signal. VHF and UHF signals are affected by foliage, and so it's one of the reasons why you might find that your range is greater in the winter than it is in the summer. Absorption by the leaves in the summer can cause a problem, so just keep that in mind. Driving along in my automobile, and I'm listening to the repeater, and the signal that I'm getting from the repeater is going up, down, up, down, up, down, up, down. What? Or I'm transmitting, and people listening to the repeater are hearing my signal go up, down, up, down, up, down, getting strong, getting weak, getting strong, getting weak. That's called picket fencing, also known as flutter. And it's caused by reflections from buildings that are coming at a regular rate because you're traveling at a certain speed, and you'll hear that. So again, you may hear this comment on the repeaters in your area. Hey, you were picket fencing back there. There's nothing you can do about it. It's a natural phenomena, but just know that it exists, and if you hear it, you go, oh, that's what he was talking about. If you're inside of a building, what's better, VHF or UHF? Well, I'd like you to think about wavelength. VHF, in our 2-meter band, the wavelength of a radio wave is approximately 2 meters, or over 6 feet. Whereas 70 centimeter or UHF radio is much smaller. And so if you have openings in buildings like windows or things like that, generally, and this is generally the case, UHF has better building penetration than does VHF because of the wavelength of the radio waves, and it's easier for them to penetrate the building. All right, now it's time for story time with Uncle Gary. I've had a lot of careers in my day, and one of the careers was as a broadcast engineer for TV stations. And I got my start working for a public broadcasting station at the then Delta College. I think it's now something Delta University or something, up in Michigan. I worked for Channel 19 up there, and PBS was very innovative back in the day. They were the first broadcast network to use satellites on a full-time basis. Before that, all of the network video and audio signals had been transmitted to affiliates by point-to-point microwave. And AT&T, the Bell folks, they were the ones that owned that system. But PBS said, we can't afford that. We're not funded that way. But we could do a capital project and build satellite uplinks and satellite downlinks at every station, and then distribute our programs via a satellite. And so PBS did that. They had actually, when I was working for them, 4 different program streams that came to affiliate stations. And they used large C-band satellite antennas. Come back to the laptop if you would there. So that's this one right here. This is a large C-band satellite antenna. And very reliable, worked very well. Well, later on, I ended up working for an NBC TV affiliate in Saginaw, Michigan, WNEM TV. And NBC saw the success that PBS had with their satellite system and said, we want to do the same thing. But they cheaped out. They said, we're not going to go with C-band because those antennas are just too big. So we're going to go to the KU band. And so we're going to put smaller dishes up, more economical, and our affiliates will have it just fine. So this is the typical size of a KU band antenna at an NBC TV station back in the 80s when I was working there. They were operating on microwave frequencies. KU band is microwave, between 11 and 14 gigahertz. And it has a very small wavelength, from 1.67 to 2.5 centimeters, whereas the C-band is much larger because it's a much lower frequency. And when you're innovating, you discover things. NBC discovered that they had problems with rain fade. Rain modules, nodules, things coming down from the rain, were just about the right size to cause absorption of those KU band signals. And so if there was a really heavy rainstorm in Saginaw, Michigan, where I was working, it would wipe out our network signal. And we just had to sit there on a please stand by slide waiting for the storm to pass. Even worse, the uplink facility was, I think, in New Jersey, and if there was a rainstorm there, it could wipe out the entire broadcast network across the United States. They put in some workarounds, some higher power levels, bigger antennas, but I just want you to know that rain fade is a phenomena. If you have DirecTV or Dish Network, you may have experienced this yourself. Where you lose your TV signal during heavy rainstorms. That's because of rain fade. So I talked to you about taking a test and the distractors. Test makers also sometimes like to fake you out. And so here's a test question that's a complete fake out. What are the effects of fog and rain, and light rain, on the 6 and 10 meter bands? Okay, we're not talking about microwaves. We're not even talking about C-band. This is much lower frequency range, 6 meters and 10 meters. So what are the effects of fog and light rain on these bands? None. Because the wavelengths are much too long, and so the raindrops don't absorb the signal like they do at the microwaves. So this is a fake-out question. They're just trying to get you to think about rain fade, but put it in the wrong context. Okay. Traveling across the United States by car, everybody do late night road trips. I would travel overnight sometimes, and I would listen to medium wave stations from a really long distance away. And that was kind of fun to be tooling along and hear WABC in New York or WLS in Chicago or some of the clear channel stations. Medium wave at night has different propagation than medium wave signals do during the day. And in amateur radio, our 160 meter band is a medium wave band, so very similar characteristics. And you can put up antennas for 160 meters. You can even feed your tower and use it as an antenna. We're not going to go into that tonight, but I just want you to know that we do have medium wave signals going on in amateur radio. And with medium wave, we're typically working with vertically polarized antennas, vertical towers, things like that. And so these are the two modes of propagation for medium wave. During the day, the signal travels along the surface of the Earth, and it's ground wave. We talked about ground wave. So that's why, for medium wave stations during the day, you can hear them 60, 70, 80 miles away, depending on your location, and then they just fade out and they go away. Whereas at night, the skywave kicks in, and you're able to utilize the skywave. We'll show you why. It goes up to the ionosphere and is refracted back down thousands and thousands of miles away. So two modes of propagation for medium wave signals. Here's a depiction of the ground wave signal during the day as it's traveling along the surface of the Earth. The wave actually tilts, you can actually see here. And we have these URLs down at the bottom. If you're curious about this phenomenon, you can go there and look at some more information about it. So this is during the day with medium wave. So at night, well, the ionosphere gets involved. And the ionosphere is the uppermost layer of our atmosphere. So we start with the troposphere down below, stratosphere here in the middle, ionosphere here up at the top. And during the day, the sun comes out. Yeah, that's kind of Captain Obvious. And when the sun comes out, then the ionization, the energy from the sun, activates the F layer, the E layer, and the D layer, DEF, going from the Earth. DEF layers of the ionosphere. And this D layer, I liken it to the dead layer. Here's our medium wave transmitter during the day. We have a skywave signal that comes off of the antenna, but it gets absorbed here in the D layer and nothing comes back down. That's why you can only hear the ground wave signal during the day. Whereas at night, you don't have the ionization of the sun. The D layer goes away. And that allows then medium wave signals to go up to the ionosphere and be refracted back down. Here's another look at it. Daytime, we have the D layer, the dead layer, D, E, the F1 and F2 at the very top. Whereas at night, it kind of goes to an E layer and an F layer. And so skywave signals are able to propagate. Notice I said the E layer here. See the E layer and the E layer? The E layer is interesting for VHF. 6 meters, 10 meters even, 6 meters. The E layer, and people don't completely understand why this is, but will form gaseous clouds at this layer. They're called E clouds. And hams have figured out that we can bounce signals off of these E clouds, whether we're trying to or not. Sometimes the bands just open up from hundreds, if not thousands of miles away. The 6-meter band is called the magic band just because of this phenomenon. And we're using what is known as sporadic E propagation. It allows us to bounce signals off of these E clouds, which will only last maybe 20 minutes or so, and then they go away. But it allows us to get communications over a long distance. And ham radio operators are opportunists. We'll take advantage of any propagation conditions we can to get signals away. Some terminology that I want you to know about: critical frequency. With the ionosphere, below this critical frequency, refraction of a radio signal will occur, and the signal will come back down to Earth. So here we have a 5 megahertz signal, it's coming back down, a 20 megahertz signal, that's coming back down. But somewhere between 20 and 100 megahertz is the critical frequency. Above the critical frequency, refraction does not occur, and the energy goes out into space. That's the reason why UHF is the frequency band of choice by NASA to communicate with the space station or astronauts going to the moon, etc., is because UHF signals will penetrate the ionosphere and go out into space. So just be aware of this critical frequency and the fact that VHF, UHF goes into outer space. For long-distance propagation on the HF bands, the high-frequency bands, it's the ionosphere that makes the magic happen. It's the F1 and the F2 layers. And how the composition of these layers is affected, as we saw, by the sun during the day and then at night. And then there's seasonal variations also. There's an 11-year cycle of sunspots. Sunspots appear on the surface of the sun and then they disappear. And we are here. At this point, we're on the downward slope of a peak of a sunspot cycle going into a trough. So in about 4 or 5 years, HF propagation will be poor. But it will come back up and be a peak again. We'd love to have these peaks like here. This would have been fantastic worldwide propagation. This was okay. This was fine. And the bands don't go totally dead, but you just have to maybe find some other ways to communicate, some digital modes, things like that, that allow you to keep operating. But sunspots are literally visible spots that you can see on the sun. And the higher frequency bands, 6 meters and 10 meters, for example, benefit from sunspots. 10 meters is a long distance band during the day. So if you want to get on 10 meters, and you do have voice privileges as a technician on 10 meters, get on the air during the day. Around noontime is the most optimum. And then you can get long distance propagation during daylight hours with high sunspots. Those two factors affect propagation on 10 meters. And here's a depiction of that with the propagation in 28 megahertz, which is 10 meters, signals going up to the highest layer, the F2 layer, and then being refracted back down. And because of that, notice the distance at which the signal travels. That's what we like. We like to go far. All right, come back to me just for a second, Bruce. So I got a chance to work for the Voice of America for 20 years between 1988 and 2008 after I left the TV realm. And I was stationed at various overseas transmitting stations. My first overseas assignment was Liberia, West Africa, and my last was Kavala in northern Greece. I never was stationed at the Philippines, but I did get a chance to visit there. And the Philippines was unique in that they had a receiver site where they would receive Voice of America signals via shortwave radio originally. Later it was satellite. And they had to get those signals down to the coast where they had a 1 million watt medium wave station beaming toward China. And the way that they did it to have reliable communications from the receiver site at Baguio to the transmitting station at Poro Point was they used something called tropospheric communications, or TROPO. Back to the slide. when you hear tropo, I say think tropical. We're using thermal layers in the atmosphere, and it can provide reliable VHF and UHF communications out to a distance of about 300 miles. And so here on the map you can see Baguio was here and Poro Point was down here. And these look like satellite antennas. Tropospheric communications is used probably in the 300 megahertz region. So it's just slightly UHF. These antennas, though, are not pointed up toward a satellite. They're pointed down toward the horizon. So using this tropospheric communication, we were able to have reliable transmission of the programs down to the transmitter site where they could be rebroadcast. So that's tropospheric communication. We use it also in amateur radio. Again, we're opportunists because sometimes tropical ducts will come and go. Tropical ducting, well, this is the normal thermal composition of the atmosphere, with warm air down at the bottom and cold air the higher you go. But sometimes there are thermal inversions where you have cold air at the bottom, warm air in the middle, and then cold air up above. This acts as a duct for radio electromagnetic waves. And you can sometimes, typically in spring and fall, you can have long-distance communications for a little period of time on VHF and UHF using this ducting, this tropospheric ducting. Here in the upstate of South Carolina, we have a repeater that does not have a PL tone on it, so any signal that comes on its input frequency will key it up. And sometimes we hear stations coming in from New Hampshire on our local repeater here, which is kind of weird. If you're going to be transmitting, excuse me, on HF, going up to the ionosphere and having it come back down, well, how about, can people in your area hear what you're sending? Typically, no, because you are in, the people here in the local area are in what we call the skip zone. Your signal goes up to the ionosphere, skips over that area, and comes back down a long distance away. However, the ionosphere is not mirror smooth. It's not perfect. It's got, irregularities in it and whatnot. And so some of that energy is actually reflected directly back toward the transmitting location. That's called backscatter. It's scattered electromagnetic waves. And so backscatter, which will be weak and fluttery, can be heard on HF. That's a propagation mode. So sometimes you can hear local stations as they're communicating with DX stations, sometimes not. It all depends on the ionosphere. I mentioned ham radio operators are opportunists. Who would have thought of this? But we have regular meteor showers coming to the Earth. Some of them are predictable. And hams discovered that 50 megahertz, or the 6-meter band, matches the nominal length of the tails of meteors. And so it's possible for hams on 6 meters to bounce signals off of meteor trails and back down to another ham who's listening and communicate back and forth. So that's one way that hams utilize just a natural phenomena in a way that you wouldn't think. Another way has to do with aurora. Aurora borealis in the northern hemisphere, aurora australis. This has to do with energy that comes from the sun that disrupts the Earth's geomagnetic field, and it makes all sorts of pretty aurora that you can see at the northern latitudes. Hams discovered that if they take their 6-meter systems and point their antennas straight north toward the aurora, you can actually beam signals off of that. So let's take a few minutes and let's listen to some auroral communications. I want to warn you, it sounds kind of freaky.
5 and 8, Aurora. 5 and 8, Aurora. Fox, November 3-2. Call is Kilo Charlie 2, Whiskey Lima, radio, over.
Yeah, QSL, nice to see you again, and beautiful signal on the Aurora. 5 and 9 Aurora here, 59 Aurora, Fox, Norway 2-5, over.
QSL, Kevin. You're also 595973. Thank you.
73 and good luck. Victor Echo 3 Echo November. I'm going to QSY up 5.
QSY is going to change frequency. That's a Canadian station, VE3EN. Changing his frequency up.
Okay, QRZ, Victor Echo 3 Echo November. Victor Echo 3 Echo November. QRZ.
Alpha Alpha 1 Tango Tango.
Alpha Alpha 1 Tango Tango. Nice to see you. Nice signal. 5 and 7, 57 Aurora. Fox Norway 25. Fox November 25. Over.
Yeah, QSL, please copy 58 Aurora. And 2 Foxtrot November 33 FN 33 over.
QSL, thanks for Fox November 33 and enjoy the opening. We're a lot of strong signals out there. Alpha Alpha 1 Tango Tango, Victor Echo 3 Echo November 73.
So Victor Echo 3 Echo November, that's his Canadian call sign. And the 4-letter designator, the Echo November 25, that's his Maidenhead locator. That's where he is located, just for people to track that. So that was Auroral Communications with signal strength that varies a lot and with high distortion. You heard it. We mentioned sporadic E propagation before. It's occasional. 15 meters and up, you can have sporadic E, but typically 10, 6, and 2 meters are the likely bands to use those gaseous clouds in the E layer of the ionosphere. We mentioned before the critical frequency of which signals will go out into space. There are 2 other frequencies to know about: the LUF and the MUF. The LUF is the lowest usable frequency you could use to communicate from point A to point B, so from South Carolina to London, England, let's say. And the MUF is the maximum usable frequency that would work between 2 locations, South Carolina and London, let's say. They vary by the time of day and the direction of the signal. The higher HF bands will work better during the day because of the sunspots. The lower HF bands work at night because the D layer goes away. So some things to consider. I'm going to show you a propagation tool you can use to help you determine if you want to work a station in England, what's the best time of day and the best band right now to actually be operating, to hear them and for them to hear you. We're talking about propagation. That's the way that radio waves get from point A to point B. And one way is through the band that exists when the sun is going down or when the sun is coming up at your location. That twilight period is called the gray line. This is a Mercator projection map, so this is it doesn't look like but there's actually a band. This is where it's dark, and this is where it's light, or vice versa, I don't know. And this twilight area here varies depending on the season, and so if you are here, for example, in the United States, you stand a very good chance of making a contact over here in the Middle East, let's say, via using gray line propagation. This is especially good for lower frequency bands, 160 meters, 80 meters, even 40 meters. That's called gray line propagation. So I mentioned that tool that you can use, and it's free, and guess who it comes from? My old employer, VOA. The VOA Coverage Area Prediction Program was something that VOA developed for transmitting stations where I worked to know what was the best frequency, the best antenna, the best bearing, azimuth, and elevation to use in order to reach a target area with the programming that we were sending them. Well, VOA Cap is online now, and it's free. And you can go there and you can play with it, and you can put in your location and someone else's location, and it'll give you this little rosette up here that'll tell you by time of day what times are going to be hot and what times are going to be Not at all. No possibility of making a contact. So it can clue you in if you're looking for a particular country or whatnot. It can tell you when you're likely going to be able to hear them and they're going to be able to hear you. So the sun is the biggest impactor on radio frequency propagation. Space weather in general has a huge impact on how radio waves propagate, especially HF. So there are online resources besides VOACAP. There's the various spotting websites. DX Heat is one of them. Spaceweather.com and solarham.net. Others here that you can get information about current radio propagation conditions. Oh, and did you know that we have our own weather person? Space weather, that is. The Space Weather Woman, Dr. Tamitha Skov, who's now a ham radio operator, but she started doing solar forecasts, and she actually now has a segment every time that she goes on YouTube with a forecast for hams to tell you about what the conditions are going to be coming up. And you can find her website at spaceweatherwoman.com, and there'll be a link to her YouTube channel where you can see her do her thing. It's really kind of cool. All right. You made it through the first section. Very good. Let's see if we can answer some questions. So why do VHF signal strengths sometimes vary greatly when the antenna is moved only a few feet?
C.
Everybody see that? Multipath propagation cancels or reinforces signals. And what is the effect of vegetation on UHF and microwave signals?
Bravo.
That's absorption. The leaves can absorb the energy. And what is the meaning of the term picket fencing?
Bravo.
That's a rapid flutter on mobile signals due to multipath propagation. And what weather condition might decrease range at microwave frequencies?
Charlie.
Rain fade, propagation. And what is a likely cause of irregular fading of signals propagated by the ionosphere?
D.
Indeed, that's that old-time World War II listening to the shortwave. Random combining of signals arriving via different paths. It's another way of looking at multipath. And what effect does multipath propagation have on data transmissions?
Delta.
Yep, the error rates are likely to go up. And which region of the atmosphere can refract or bend HF and VHF radio waves?
Charlie.
Bravo.
It is Charlie. It's the top layer. HF.
Oh, HF.
Yep. The ionosphere, yep. So what is the effect, here's our trick question, what is the effect of fog and rain on signals in the 10 meter and 6 meter bands?
Bravo.
Yeah, there is little or no effect on those, yep. And why are simplex UHF signals rarely heard beyond their radio horizon?
Charlie.
Yes, UHF signals, they go out into space. They're usually not propagated by the ionosphere, not refracted back. So what is a characteristic of HF communication compared with communications on VHF and higher frequencies?
Charlie.
Charlie.
Yeah, long distance ionospheric propagation is far more common on HF. That's what I love to do. And what is a characteristic of VHF signals received via auroral backscatter? You heard it.
Bravo.
They sound distorted and the signal strength varies considerably. And which of the following types of propagation is most commonly associated with occasional strong signals on the 10, 6, and 2 meter bands from beyond the radio horizon?
Delta. Bravo.
So we're talking about 10 meters, 6 meters, and 2 meters. So these are close to VHF frequencies, and this is where we have the gaseous clouds in the E region, sporadic E. Gray line is more for lower frequency signals, 160, 80, and 40 meters. All right, which of the following effects may allow radio signals to travel beyond obstructions between the transmitting and receiving stations?
Alpha.
Yeah, that's knife edge diffraction. And what type of propagation is responsible for allowing over-the-horizon VHF and UHF communications to ranges approximately 300 miles on a regular basis?
Alpha.
That's what we did in VOA. Tropospheric
That's where I got
ducting.
confused before, yeah.
Yep. So what band is best suited for communicating via meteor scatter?
Bravo.
It is. It's 6 meters because it matches the average length of the meteor tails. And what causes tropospheric ducting?
Delta.
Tropo, think thermal, think temperature inversions in the atmosphere. And what is generally the best time for long-distance 10-meter band propagation via the F region?
Alpha.
So it's going to be during the daytime, so from dawn to shortly after sunset, and we want high sunspot activity, so indeed alpha. And which of the following bands may provide long-distance communications via the ionosphere's F region during the peak of the sunspot cycle?
Alpha.
You have privileges as a technician on both of these bands, 6 and 10 meters. And why is the radio horizon for VHF and UHF signals more distant than the visual horizon?
Charlie.
The atmosphere refracts radio waves slightly, about 15%. Great. All right, let's continue on. Section 4.2, Antenna and Radio Wave Basics. And the most common type of antenna that we have is the dipole antenna. I'm going to go ahead and mute y'all because sometimes the little noises and whatnot are distracting for me. There we go. So a dipole antenna is what you see here on the screen. It's fed via a coax cable typically in the center. There's an insulator here in the center. So the two halves are not connected together. Each of these is a quarter of a wavelength long at the frequency of design. So a quarter wavelength here and a quarter wavelength here. Quarter plus a quarter is a half. So this is why we call this a half wave dipole antenna. And this is being fed at the center, and we have insulators here at the end and here because these are some high voltage points actually at the end. We'll show you that. So a dipole antenna is the fundamental element of most antennas. Even directional Yagi antennas, things like that, have probably a dipole antenna as the driven element. And we mentioned that it's an electromagnetic wave, that radio waves are. It consists of an electric field and a magnetic field, and they are at 90-degree angles to each other. And the interaction of these two fields creates the electromagnetic wave. And so this is graphically how it looks. Note that the E field and the magnetic fields are at 90-degree angles to each other. So in this case, the E field is the one that's going up and down, and the magnetic field, or the B field, is going side to side here. Now, we talk about an antenna's polarization. Is it polarized vertically, or is it polarized horizontally? And that corresponds to the electric field. The electric field polarization is what we're concerned about, and it just so happens that also corresponds to the orientation, physical orientation of the antenna. So a dipole antenna, I do this bring my hands out to simulate a dipole, that's a horizontally polarized antenna, whereas one going up and down would be a vertically polarized antenna. So antenna polarization, again, this is horizontal, this would be vertical. And in each of these cases, the electric field is also horizontally polarized. In this case, it's vertically polarized. So here we have a car, or as some people call ham radio cars, porcupines, with lots of antennas. Which are these? Are these vertically or horizontally polarized? Anybody? They're going up.
Vertically.
Yeah, they're going up and down, so these are vertically polarized antennas. And one thing that hams, if they want to operate VHF and UHF weak signal activity, but they don't want to be interfered with by the FM mobile transmitters, things like that, they have chosen for weak signal activity on VHF and UHF to go horizontal. When they do that, you eliminate reception by about 20 to 30 dB of the vertically polarized signal, so it reduces the noise and helps weak signal propagation. So just keep that in mind. Here is, for example, a horizontally polarized VHF or UHF Yagi. I can't quite tell, depending on the dimensions. It's got a dipole antenna back here, which is the driven element, where the energy, and then it's got some passive elements. In the front, they're called directors, and this one in the back is called a reflector. They're slightly different in length. So this is a directional antenna with direction pointing in this direction over here. That's where signals would be received best and would be transmitted to best. And as I mentioned, there is isolation between horizontal and vertical polarizations. And satellite manufacturers in Europe started using this. They'd build satellites up in space, and they'd polarize half of the signals on horizontal, half the signals on vertical. Back down on Earth, you'd have a small low noise block converter like this, and inside there would be a horizontal antenna and a vertical antenna, and it allowed them to double the amount of channel capacity on some of the first television satellites, for example, in Europe, because of this cross-polarization isolation. Now, on high frequency radio from 3 to 30 megahertz, you can have both vertical antennas and horizontal antennas. Well, does that mean that I'm only going to, if I have a vertical antenna, I'm only going to hear vertical signals? Actually, no, because of the ionosphere. So what happens is with a transmitter, whether it's horizontal or vertical, when it goes up to the ionosphere, when it comes back down from the ionosphere, it has both horizontal and vertical characteristics. It's tumbled. It's said to be an elliptical wave coming back down. So either a vertical or a horizontal antenna can typically be used at the far end and with similar results. Now, I will say I have had personal experience with signals coming from South America where I could only hear them on a vertically oriented antenna, and I couldn't hear them on my horizontal antennas. So that was an extreme example. Normally, though, the elliptical wave is created and it's tumbled, and so either type of antenna for HF, for high frequencies, will work just fine. So let's talk about some theory here. If you had a point source, a point in space, and it was radiating energy, that would be known as an isotropic radiator. You see here at the middle, there's that point, and energy is radiating out equally well in all directions. The problem is we can't build such an antenna because of reflections coming from the Earth or from buildings or whatnot, but it is a theoretical engineering reference. And so this is used in comparing antennas against a known quantity, and that being the isotropic radiator. And we use the isotropic radiator as a reference in order to measure or identify antenna gain. By this, we control the pattern of the antenna. And by controlling the pattern of the antenna, then we can control how well it receives and transmits in certain directions. Let's walk over to the smart board, and let me show you some examples of this. I'm walking kind of slow because my knee is still a little sensitive, but hopefully I'll be upright here. All right, so let's start over here on the whiteboard. Oops, and if I go in the right direction, hello, there we go. We have our balloon. We've got a balloon down here. We're going to show you that in a second. But here we have a balloon. And I'd like you to think about this as the radiation pattern from an antenna. And the Earth, let me draw the Earth a little higher. So the Earth is here. So the antenna is here. And note that the energy from the balloon, the radio wave pattern, goes out here. This is the range of reception and transmission from this antenna. A lot of the energy is just going up into space, is kind of being wasted. Well, what if we were able to exert forces on this radio wave to smush the balloon down? And if we did that, I guess I'm going to start here. Well, note now the range is here and here. We would say with this smush down pattern, the gain is higher in these directions because we were able to control how the radio pattern, the radio wave was being propagated. Come over to our little balloon over here. Let me put this back. Same thing here with the little balloon. You can maybe see it another way. If I press down on it, see how it gets wider out there? So let's say this is 1 cubic feet of air in here. I don't know what it is, but that's about it, okay? And if I push it down, there's still 1 cubic feet of air there, but it's going in different directions. Well, liken the cubic feet of air to power density. The power density of this antenna, where most of the energy is going up, is the same as the power density overall of this antenna where I'm affecting the pattern. Keep that in mind because that's a test question. All right, let's go on back. So Yagi antennas or beam antennas are directional antennas, and as I mentioned, they typically have a half-wave dipole antenna as the driven element. That's where the radio energy comes from the transmitter. And then you have shorter elements going toward the front called directors, and maybe one or more reflectors behind it. And so this antenna is directional in this direction over here, and it has gain over just a dipole antenna, or even more gain over an isotropic radiator. So that's what we're talking about with gain. We call this a Yagi antenna. It's actually based on development work done in Japan. Actually, Mr. Yagi was the senior professor, Mr. Uda was the technician. Mr. Uda did all the work, and Mr. Yagi got all the credit. Okay, but you can take a look here, the true story of the Yagi antenna. A 6-meter 3-element Yagi, it would look something like this. You'd have a half wavelength dipole antenna in the center. This would be the driven element. You'd have an element up front, the director, which would be about 5% shorter. And you'd have a reflector element back here about 5% longer. This is the reflection element, and this antenna would have gain off in this direction. So as we look at it here, I don't know if we're looking at a side view or a top-down view. Here we can see the supporting mast. This antenna is for HF, for high frequencies. It's a tri-band antenna for 20 meters, 15 meters, and 10 meters. And this is horizontally polarized. So again, it's got a driven element here in the middle, a director, a shorter antenna in the front, and a reflector out in the back. And when we say that an antenna has gain, you could do math. You can say this more microvolts than the other, but we use decibels. Decibels is actually easier when you're making reference to a standard. And that standard could be the dipole antenna, or it could be the isotropic antenna. And these are the ones that I want you to know about. For power gain, 3 dB is 2 times the power. So with an antenna with 3 dB of gain and you feed it with 100 watts, it would be like feeding 200 watts to a dipole, for example. Or 6 dB is 4 times, and 10 dB is 10 times. So these are the ones that I want you to be aware of. Also, if you have a radio and it's got an S meter, the S meter is calibrated in dB over here on the right side and in S units on the left side. Each S unit corresponds to about 6 dB. So you can actually use the S meter in your receiver to make gain measurements. So how do you get gain? Well, with a vertical antenna, this is the typical omnidirectional pattern. The vertical antenna is in the middle here, up and down, and it's a donut shape around the antenna. So this is an omnidirectional pattern. Whereas if we were using a Yagi-Uda antenna, this is the kind of pattern you get. You have a main lobe going out here. This is where the most gain is. The antenna is facing this direction. This is the back side of the antenna. There's some gain in that direction, but less. So the ratio of gain to the front, gain to the back is called the front to back ratio. And there are some side lobes where you have some minor gain, and there's some nulls in here as well where you don't receive or transmit very well at all. So what we're doing is we're just controlling the pattern of the antenna to move the major lobe out so that we get gain in a particular direction. And main lobe, side lobes, nulls, and the ratio of gain in the forward to the opposite direction, that's the front to back ratio. So I mentioned to Thomas earlier before we got started, I was going to introduce this antenna. The dipole antenna, which is a quarter wave on one side and quarter wave on the other, if you mount it at about a half wavelength above the ground, that's optimum for DX, for long distance transmission. But if you mount them lower than that, in fact extremely lower, what happens is the antenna azimuth elevates. So here we are between half and a quarter of a wavelength, so we have slightly elevated lobes. If we go to the extreme and go down to 0.125 wavelengths above ground, a very low dipole antenna, most of the energy goes up, directly up to the ionosphere. Why would you want that? Well, let's say, as with Thomas, he lives in a mountainous area with terrain blocking and whatnot. In this way, energy can be focused up to the ionosphere and then bounce back down on the other side of the mountain, and so other people in the other area in his region could be able to receive his signals. The military uses NIVIS antennas for tactical communications in mountainous regions because VHF and UHF won't go through the mountain. It's blocked. But NIVIS antennas sending energy up and having it come back down again work just fine. All right, some more questions and then we can take a break. So what happens when antennas at opposite ends, now note this, of a VHF and UHF line of sight radio link are not using the same polarization?
B, Bravo.
For VHF and UHF, the polarization is a real issue. You've got to make sure you're using the same polarization. And which of the following results from the fact that signals propagated by the ionosphere are elliptically polarized?
Bravo.
Yeah, it doesn't matter if you use a vertical antenna or a horizontally polarized antenna, they both may be used for transmission and reception. And what is the relationship between the electric and magnetic fields of an electromagnetic wave?
D, delta.
Yes, they are at right angles or orthogonal. And what property of a radio wave defines its polarization?
Alpha.
The electric field. And what are the two components of a radio wave?
Charlie.
C.
Yep, the electric and the magnetic fields together make an electromagnetic wave. So which decibel value most closely represents a power increase from 5 watts to 10 watts?
3 dB.
That's times 2 or 3 dB. And which decibel value most closely represents a power decrease from 12 watts to 3 watts?
Charlie.
That's 6
D,
dB
right.
decrease, or so it's minus 6 dB. And which decibel value represents a power increase from 20 watts to 200 watts?
Alpha.
That's 10 dB, indeed. All right, and what is antenna gain?
I'm gonna go with Charlie.
And you would be correct.
I'll second that.
The increase in signal strength in a specified direction compared to a reference antenna, and it's typically measured in dB. All right, you made it. Let's go ahead and take 5 minutes, get up, stretch, move around, and come on back, and we'll finish up with section 4.3. and welcome back. Glad to have you with us. We're continuing on in Chapter 4 of our Technician Class License Manual, and we're on to Section 4.3, which is all about feed lines, the cables that take energy from our transmitter to the antenna, and something called SWR, or Standing Wave Ratio. So we briefly touched on the topic of impedance in previous classes. Impedance is the combination of a resistance and a reactance. Could be inductive reactance, could be capacitive reactance. And when they combine together, we have an impedance. And all transmitting system sections or parts have nominal impedances. So the transmitter, the source of RF energy, typically has a 50 ohm output impedance. Feed lines also then have a characteristic impedance. Coaxial cable can be 50 ohms. That's the most popular for use in amateur radio. 75 ohm coax exists. Cable TV uses 75 ohm. And it's said that 75 ohm is better for reception, 50 ohm better for transmission. That's a general thing. And then there's other types of feed lines, 300 ohm or 450 ohm. We'll look at those. And then there's impedance matching with the antenna. The antenna should also have a 50 ohm impedance, input impedance, but it may or may not. And that impedance mismatch can cause a reduction in the amount of power that is transmitted from the antenna and out into space. So impedance matching is always the desirable thing. And this is what we talked about with the impedance being a combination of resistance on one axis and reactance on a 90-degree axis, and so this is the magnitude of the impedance in this case. We don't go deep into it in the technician class. We will more so in general and extra classes. So again, we talked about feed line impedances. Coaxial cable, the most common, is 50 ohms. This is ladder line, kind of looks like the old TV twin lead with two parallel conductors going out flat to an antenna in this case, and feeding the antenna that way. Feed line types are a coaxial cable, like you might have for your cable TV, but we also use it then in ham radio for transmission line. Flat twin lead, and then flat ladder line. These are different types. We want to impedance match. We want to have the output of the transmitter feeding a 50 ohm feed line, feeding a 50 ohm antenna. Well, right off the bat, here we have our half-wave dipole antenna, and the nominal input impedance of an antenna that's tuned to the particular frequency with a quarter wavelength going this way and a quarter wavelength going that way, the impedance of the antenna is nominally about 73 ohms. So that's not 50 ohms. And so already we know there's going to be a slight impedance mismatch right here between 50 ohm and dipole antenna. We'll talk about that here in just a second. When feed line is involved, you're always going to have losses, signal losses at the end of a 100-foot run, for example, and that loss shows up as a minor heating of the cable. It's not going to catch fire, but energy is being lost as heat in the cable. The number one rule for coaxial cable, probably all cables, but for coax for sure, is to keep it dry. Moisture increases power loss, and you don't want that. So keeping transmission line, coaxial cable, or other types dry is important. Now, what about the broadcasters? They're transmitting a 100,000 watt signal or 50,000 watts or whatnot. What are they using? Well, they're not using coaxial cable, but they're using something called air-insulated hardline. And you can see various flavors of this hardline. You can get it in 50 ohm or 75 ohm impedances. It's got an inner conductor, which is a tube here, copper tube. It's got insulators to keep it away from the shield, the outer shield here. And the inner dielectric material is primarily air, except you can't use just air. Typically you use nitrogen because you want to keep moisture out, because remember, moisture increases losses, and losses make heating of the cable. Or you can use dried air. Some broadcast facilities, they have air dryers that you can then pressurize the line. And the line is pressurized with special connectors on it. It's like a tire on your car. You want to keep pressure on it. And if there are any small leaks, the pressure will keep moisture out. So that's another factor as well. So even a leaky transmission line is better than not having the pressure on there at all. Whether you have coax, whether you have 450 ohm ladder line, whether you have air insulated hard line, the higher you go in frequency, the greater the loss in dB, and it's typically dB per 100 feet. So as you see here, we have cable loss in dB, and we have frequency in megahertz going up here, and some various types of coaxial cable. Note some are better than others, especially at the higher frequencies. They have lower loss, but notice they all have a trend line where their loss goes up the higher you go in frequency. For amateur radio, RG8X is a popular cable. RG58 was a popular cable, it's not so much anymore. RG213 is a popular cable. Note the difference in physical size, though, between RG58 and RG213. And one characteristic this larger cable has is that it has lower losses at all frequencies versus RG58. So that's one characteristic. You can also handle higher power levels, but that's important. So impedance matching, as we talked about, if we have the source impedance and the characteristic impedance of the feed line and the antenna impedance all the same, then all of the energy coming from the transmitter will be radiated from the antenna. That's our perfect condition. I want you to think about the ocean coming up against a cliffside, wherever you might be, and what happens is the wave comes in toward the cliff, it'll hit the cliff and bound back. That's called the rebound wave. The wave comes in and bounces back. Well, the same kind of energy bounce back goes on in a transmission line. A radio frequency signal comes from the transmitter, it's sent out over the feed line, it hits an antenna or a mismatch at the other end. This is the worst case. This is saying that all of the energy, see that big hump that represents energy, is going out from the transmitter and it's all being reflected back toward the transmitter. Nothing is being radiated. Here we have a similar situation where some of the energy is being radiated, see it's going off to the right, but some of it is being reflected back. Note that the polarity change, that is an indicator of the impedance being lower at the antenna than the feed point. That actually happens. The polarity will change. Here's another one with energy coming back. This is indicative of a higher impedance load than the feed line, but still energy is coming back. It just didn't change polarity. The absolute worst case you can have is either hitting an open circuit at the far end or hitting a short circuit at the far end. In that case, all of the energy will be reflected back. In one case with a short, it changes polarity. In the other case with the open, it stays the same polarity, but all of the energy comes back. What we're looking for, though, is this, where the energy leaves the transmitter, goes down the transmission line, is absorbed by the antenna and radiated out into space. And there's no reflected power. There's no rebound wave coming back from the antenna. That's what we would like to achieve, if at all possible. I don't know if you were ever involved in CB radio or whatnot, but standing wave ratio is a big topic of discussion in that. I'm going to show you a standing wave. So here we have energy coming from the transmitter on the left. That's the light blue signal kind of traveling from left to right. You can kind of see it going along there. And then we have a rebound wave coming back from the antenna. That's a mismatch. See, that's the red that's coming back. That's the energy coming back. And where they add, when the voltages add between those two waves, you create this black wave that is not traveling. It's standing on the transmission line. High voltage positive, high voltage negative, high voltage positive, high voltage negative. This is, of course, happening very, very fast. This is just a reproduction. But it shows you this is what we call a standing wave. And we're trying to minimize that. If we have all of the energy being absorbed by the antenna, you will have no standing wave. But in this case, where you have as much energy going out as coming in, you have the maximum standing wave. This is a concept that's been known for a long period of time, both in radio frequencies and others. AT&T, they developed a mechanical model, and if you got some time, there's a URL down here at the bottom for a YouTube video on AT&T's mechanical wave behavior model that shows you exactly what we've been talking about. But remember, our goal is to have no reflected power, because if we have no reflected power, then we have no standing wave. And a perfect match is what we call 1-to-1. That means that the load is 50 ohms if the feed line is 50 ohms. In this case, it's slightly above that. It's 1.14, but that's pretty darn good. Always in a standing wave ratio, the bigger number is going to be first. So you can have a 2-to-1 standing wave ratio or a 3-to-1 standing wave ratio. You can never have a 1-to-3 standing wave ratio. That doesn't work. But it's showing you the ratio of impedances. And you can buy meters like this one. It's installed between the transmitter's output and the antenna feed line, and by setting it up and calibrating it, you can read the standing wave ratio. Now, this is just one example. There are all sorts of different other types of power meters, standing wave meters. Not all meters are created equally. Keep in mind that some of them are designed for just low power levels. Some of them are designed just for high frequency. Some of them are designed just for CB, the 27 megahertz region. They're not accurate anywhere else. Some are good for VHF and UHF, but not for HF. So you always have to keep that in mind, that not all standing wave meters are created equally. And again, we're using it to hopefully tune our antenna to get a 1-to-1 standing wave ratio. If you go to a ham fest, I just got back from Hamcation in Orlando this last weekend, saw a bunch of these directional watt meters. Bird was one of the popular manufacturers. You can't quite see it, but there are two ports on this meter. There's a port over here, and there's a port on this other side over here. I call this the goes into, and this is the goes outa. And you feed the transmitter signal to the goes into, and you connect this over here to your antenna, and you can read the forward power in watts. And by installing one of these power slugs into this slot, you can see a spare slug is sitting over here on the side. And notice there's an arrow on this slug pointing in that direction, which means that we'd be reading the forward power, the power going toward the antenna. If you take this slug and turn it 180 degrees, then you're reading the reflected power coming back from the antenna. And if you know those two levels, there's a table on the back where you can calculate the standing wave ratio. The voltage standing wave ratio, is sometimes called, is really of concern with modern solid-state transmitters. It wasn't so concerning with vacuum tube transmitters because they had output networks that could compensate for a wide range of standing waves, and it didn't cause a problem. But with solid state, with transistors, then we have to be concerned about it. As I mentioned, 1-to-1, that's our goal, that's perfect. 2-to-1 is acceptable. Anything under 2-to-1 would be okay. Danger is above 3-to-1, and by that I don't mean you're going to let the smoke out of the radio, but at 3-to-1, typically solid-state radios will say, oh, there's a problem, and your 100-watt radio will suddenly become a 50-watt radio. It will reduce the output power. The higher the VSWR goes, the lower the output power of the radio. It's protecting itself. It's protecting the output devices in it. And so even a modern radio like the 7300 from ICOM here will have reduced power output from standing wave ratios above 2:1. Okay, well, I've made all the adjustments on the antenna, but my dipole antenna, like you saw there, has got 73 ohm input impedance. I can't adjust that. What can I do? Well, you can use something called an antenna tuner, also known as an antenna coupler. Here's one from Kenwood. The radio back here that I showed you, the 7300, has one built in. It comes in the radio, and that's a good thing. For a solid-state radio, it should have an antenna tuner built in. What this does is it generates a rebound wave. That energy that's coming back from the antenna is adjusted here with the antenna tuner, and it sends it right back out to the antenna again. So coming from the antenna, going back out to the antenna again. This happens at the speed of light. So it doesn't really cause any issues, and it makes the transmitter happy. The transmitter will see a 1-to-1 standing wave ratio and say, oh, I can output full power. So that's what an antenna tuner is all about. And it's made up of inductors and capacitors in a network arrangement. Here's an L network with a series inductance coil and a parallel variable capacitor. This might be one type of matching system, or it can be a pi network. It looks like the Greek letter pi with 2 variable adjustments on it for a wider range of adjustments. Okay, let's answer some questions. Which of the following should be considered when selecting an accessory SWR meter?
Alpha.
Yeah, they're not all made the same, so you got to consider the frequency and the power level at which the measurements will be made. So what reading on an SWR meter indicates a perfect impedance match?
Charlie.
1-to-1. Not full scale. Why do most solid-state transmitters reduce output power as SWR increases?
Alpha.
It's to protect its output amplifier transistors. And what does an SWR reading of 4-to-1 indicate in general?
Delta.
An impedance mismatch, a pretty good one. Or bad one. All right, what happens to power lost in a feed line?
Charlie.
It is converted into heat. And what is a benefit of low SWR?
Bravo.
Reduced signal loss certainly on transmission, but it also helps your reception as well. And what is the most common impedance of coaxial cables used in amateur radio?
Bravo.
50 ohm. Yep. And why is coaxial cable the most common feed line for amateur radio antenna systems?
Alpha.
It's the American way. It's easy to use and it requires few special considerations. We like easy. And what happens as the frequency of a signal in coax is increased?
Delta.
As the frequency goes up, the loss will also go up. dB per 100 feet. And what can cause erratic changes in SWR? You have to think about this.
B.
Yeah, a loose connection could do it. It could be intermittently open or shorted. And which of the following types of feed line has the lowest loss at VHF and UHF? What do the broadcasters use?
Charlie.
They use air-insulated hardline. Hams do too. So what is standing wave ratio?
A.
Yes, it's a measure of how well a load is matched to a transmission line. All right, real short, section 4.4, practical antenna systems. Your HOA is not going to allow you to put up one of these. This is from the VOA transmitting station in Greenville, North Carolina. We were talking about it earlier. I think that A-Site is still operating there in Greenville, and they have some of these 400-foot tall curtain antennas with a 20 dB or 100 times power gain. Awesome. But yeah, no, you can't put it up in your HOA community. So think about, well, maybe a dipole. Remember we talked about the dipole being fed at the center with a quarter wavelength on each side. It's what we call a resonant antenna. It's designed around one frequency of operation, and its overall length is a quarter plus a quarter, so it's a half wavelength. If you're going to convert meters, remember we work in meters in science, just know that 1 meter is the same as about 39 inches. So how long is a dipole antenna in feet? I think there's a formula in the book, and then there's this one. This is the more popular one, I think. 468 divided by the frequency in megahertz will give you the length of the half-wave antenna in feet. Then whether the wire is bare copper or whether the wire has an insulated jacket, a plastic jacket on the outside, will change the length. And that's what that V, or velocity factor, is all about. With a plastic jacket on it, the antenna will be slightly shorter, maybe 5% or so. So this is how you can calculate how long a dipole antenna in feet will be. 468 divided by the frequency in megahertz. It will get you started. Also, there's what we just talked about up here, 468 divided by F, the frequency in megahertz. If you want a quarter wavelength vertical antenna, it's 234 divided by F. And to get the answer in inches, you take that feet and of course multiply it by 12 inches. So this will give you half wave antenna in inches if that's what you need, or quarter wave in inches if that's what you need. And when we're looking at a dipole antenna and we're looking at voltage and current distribution on that antenna, that's what this is all about. The high current point of a dipole antenna is at its center. That's what the blue represents. You see the current minimum, maximum and minimum? And the high voltage points of a dipole antenna are at the ends of the antenna. That's what the V is representing. High voltage here and high voltage out here. So this is a normal phenomenon. We say, or at least according to Mr. Moxon, you want to get the current points up as high as you possibly can. So that's why an inverted V dipole antenna can sometimes work as well as a flat dipole antenna if you can get this point at the center up as high as possible. That's a key, get the current point, because that's where the energy is being radiated from. And also, here's a dipole antenna. We're looking top down on it now. It's kind of vertical to our orientation here. Here's the dipole antenna. And you can see its radiation pattern off the sides of the antenna. Note there's not much being radiated at the ends of the antenna. That's normal. So your positioning of the dipole antenna is important. If you want to work Europe with that antenna, you have to have it broadside to Europe. If you have the ends pointed toward Europe, you're not going to get them. It's just not going to work. And so this works for transmission. The same pattern exists also for reception. So when a signal, an electromagnetic wave comes into a dipole antenna, it induces a voltage. The electric field induces a voltage into the antenna, and that's transmitted back to your receiver. That's how you can hear. And the directionality is the same for both transmission and reception. So looking down here on our the axis of the antennas here, broadside, this figure 8 pattern, the strongest signal is broadside to the antenna. And the size of the antenna has to do with the frequency of operation. So higher frequency antennas are going to be shorter or smaller. Lower frequency antennas are going to be longer or larger. So some key concepts to remember: the longer an antenna is, the lower its resonant frequency will be. The shorter the antenna, the higher its resonant frequency will be. And an antenna is a resonant circuit at the desired frequency of design. And it could be likened to either a series resonant circuit. Remember, a resonant circuit has an inductor and a capacitor. So here's a series resonant circuit, and this R in this case is the radiation resistance of the antenna. It's what the antenna does work with. This is what radiates the signal out into space. Here's a parallel resonant antenna. There are models that work either way. We're going to talk more about the resonance concept as we go along. Now, quarter wave vertical antennas are kind of like a dipole antenna that's going up with 1/4 of the wavelength and sideways with the other quarter wavelength. So you're feeding in the middle, but you have one vertical element and then these radials or counterpoises going off to the side. This is a quarter wave vertical antenna. Very common, very popular for VHF and UHF. So when you get your technician license, you can build these very easily, and they're very good. They're practical antennas. Now, they're going to, at the ham store, they're going to want to sell you a 5/8 wave antenna. 5/8 wave antennas require special compensation for impedance matching at the base. But the thing is that they have a lower angle of radiation toward the horizon. So whereas let me do it this way. the quarter wave angle of elevation might be like this. The 5/8 wave antenna elevation might be lower down. That's where they say the 5/8 wave antenna has higher gain than a quarter wave, if that's where you want the gain to go, which typically is the case. And if you're going to mount an antenna on your car, the best place you can mount it is the dead center of the car, because that provides the most uniform pattern. If you mount it off to a corner, it'll still work, but your antenna system might be somewhat directional. So as you turn away from something, your signal strength might go down or up depending on which way you're going. I mentioned that the antennas are resonant circuits. They have both inductive reactance and capacitive reactance, and they equal out at the design frequency. This is the formula for a resonant circuit. I'm not going to make you use it. I'm not going to make you work it. We don't do that here. But I want you to notice the relationship. 1 over, and here's an L, and here's a C. Ignore everything else. What this means is that as we increase inductance, or as we increase capacitance, or we increase both, the resonant frequency F is going to go down. If we increase inductance, if we increase capacitance, the resonant frequency of that antenna is going to go down, which is how we have antennas on cars for the HF bands. Because a vertical antenna quarter wave for 80 meters would be 20 meters high. That's not going to work. But if we add an inductor to the center of the antenna, like this, it makes the antenna look electrically longer. And so that's how we can get HF antennas on cars, by using these big coils, because of the formula we just saw. Now, the bandwidth of the antenna, the usable frequency range over which you can transmit, gets much smaller. You don't get something for nothing. So that's what happens here. Our old friend, the Yagi-Uda antenna, we looked at these before. The half wavelength dipole here in the middle, the director here with about 5% shorter, and the reflector on the back about 5% longer. There's also a concept called a cubical quad antenna, which has a full wave loop here as the driven element, and then it has directors 5% shorter, 5% shorter, and a reflector 5% longer. These are handy for certain applications. They're a little more mechanically difficult to build, but cubicle quads have a certain following in amateur radio. It's a gain antenna. Another gain antenna is, of course, the dish that you might use for a satellite system. Satellite antennas have very, very high gain, 30 to 40 to 50 dB depending. And so here we have the main lobe of the antenna and some side lobes coming out. Just know that a satellite antenna is a high gain antenna. So matching an antenna to the proper impedance to get the best standing wave ratio, we use something like this, an antenna analyzer. An antenna analyzer has got a built-in signal generator for a radio frequency signal, and it can measure impedance and the resonant frequency of the antenna directly. There are all sorts of different types. This is one that was sold by MFJ, Rig Expert, and others also make similar ones. Know this, when you get your first radio, it's probably going to be an HT, and it's probably going to come with a rubber duck antenna. It's not a very effective antenna. It will work, it'll get a signal to the repeater, but aftermarket antennas or an outdoor antenna or a mobile antenna for your car, if you can interface it to the radio, would work much better. The rubber duck antenna inside of a car is very poor because the signal is shielded by the vehicle. And typically on the common HTs now, this connector here is called an SMA connector. Here are various connectors. This is the SMA connector. Could be a male or a female depending on the type of radio you have. There are other connectors though used for amateur radio. The N connector, named after Mr. Neal of AT&T. The BNC or bayonet connector is also popularly used. But the most popular connector in ham radio is this. A UHF connector is one of its names. It's also called a PL259 from the military derivation. It's the most popular connector used for HF and also for VHF and UHF by some manufacturers. And you install a PL259 on the end of a coaxial cable using a heavy-duty soldering iron and rosin core solder. At least this has been the standard in the past. I prefer personally a crimp connection, PL259. You have to buy the crimp tool and you have to buy special crimp connectors. But for me, you solder the inner conductor, that's fine, but you crimp the shield. I have 100% reliable connections using crimp connectors. People will tell you I did not have 100% reliable connections with my soldered joints. Here's a closer look at that N connector from Mr. Neal. It's best for use above 400 megahertz for a couple of reasons. It's double shielded. There's an inner conductor here at the center, then there's a shield very close by, and then there's an outer shield as well, so it's very well shielded. See, there's a rubber gasket in here. This connector is waterproof. PL259s are not waterproof, and remember I said water and coaxial cable don't work well together because you have higher losses. So this is an improvement, the N connector. They're a little more difficult to put on, however. If you're going to be putting a connector on or doing any work in electronics, never use acid core solder. It's kind of hard to find anymore, but it was a solder that was used for plumbing. For electronics, we want rosin core solder. Because that has a built-in flux material, the rosin, that will help the lead in the tin, which you're heating up and melting, to flow and get a good solid connection. A bad solder joint can be intermittent, can be trouble-prone, can cause you all sorts of aggravation. A bad solder joint is dull, it's rough, it's lumpy, it may show cracks like you see here. This is also known as a cold solder joint. You don't want one of these. All right, let's answer some questions. What antenna polarization is normally used for long distance CW and single sideband contacts on the VHF and UHF bands? Think back to something I showed you about the porcupine. So we want to do, yeah, they're going to use the opposite of vertical, they're going to use horizontal for weak signal, long distance. And when using a directional antenna, how might your station be able to communicate with a distant repeater if buildings or obstructions are blocking?
Bravo.
Yeah, it's like my WSPA reception problem that we worked up. And where should an RF power meter be installed?
A.
In the feed line between the transmitter and the antenna. And which of the following is used to determine if an antenna is resonant at the desired operating frequency?
Bravo.
Like I showed you, that MFJ unit and antenna analyzer is what we use.
Are those people still in business?
No, they are not. They went out of business this last year. So which instrument can be used to determine SWR?
Delta.
Remember the directional watt meter with the goes in and the goes out and the slug that you could turn to read forward power and then reverse power, and you can look at the chart on the back and then you can calculate SWR. I like the iambic pentameter, if anybody's an English major. All right, which of the following causes failure of coax cables?
Alpha.
Moisture. You want to keep the water out. Why should the outer jacket of coaxial cable be resistant to ultraviolet light?
B.
Delta. Yeah.
Delta. Ultraviolet light can damage the jacket and allow water to enter the cable. No good. And what is the disadvantage of air core coaxial cable when compared to foam or solid dielectric types?
C, Charlie.
Charlie.
You gotta use nitrogen, or you gotta use dry air. You have special techniques to prevent moisture in the cable. And which of the following types of solder should not be used for radio and electronic applications?
A, alpha.
Yeah, acid core solder. It'll eat right through the PC boards. And what is the characteristic appearance of a cold tin lead solder joint?
Charlie.
A cold solder joint, a rough or lumpy surface. And what is a beam antenna?
Charlie.
C, Charlie.
It's an antenna that concentrates signals in one direction. And which of the following describes a type of antenna loading?
B.
No, and I didn't use the term loading, and I should have. To
A.
make, it's A, in order to make a mobile antenna for HF on a car, you have to add that coil in the middle. That's called
Gotcha.
inductive loading. Another way you could do it is add a capacitive top hat to the top of the antenna. That would be capacitive loading. So it's electrically lengthening by inserting inductors in the radiating elements. That's one type of loading, making it look electrically longer. So which of the following describes a simple dipole oriented parallel to the Earth's surface?
Bravo.
It is a horizontally polarized antenna. And what is the disadvantage of the short, flexible antenna supplied with most handheld radio transceivers compared to a full-size quarter wave antenna?
Alpha.
Yeah, the rubber duck antenna has very low radiation efficiency. It doesn't radiate a lot of signal. And which of the following increases the resonant frequency of a dipole antenna?
Alpha.
No. As the frequency goes up, the antenna gets shorter.
Oh.
Shorter antennas for higher frequencies. Which of the following types of an antenna offers the greatest gain?
Delta.
From these, it would be the Yagi or Yagi Uda. And what is the disadvantage of using a handheld VHF transceiver with a flexible antenna inside a vehicle?
Alpha.
Yep, signal strength is reduced due to the shielding effects of the vehicle. And what is the approximate length in inches of a quarter wavelength vertical antenna for 146 megahertz? I'm not going to make you do the formulas, but I gave them to you. Anyone want to hazard a guess?
I'm going to say C.
And you would be correct. 19 inches is the approximate length of a quarter wavelength vertical antenna for 2 meters. And what is the approximate length in inches of a half wavelength 6 meter dipole antenna? So you saw the formulas, and you can go back and check them out. It's 112 inches. And in which direction does a half wavelength dipole antenna radiate the strongest signal?
Delta.
Broadside to a dipole, broadside to the antenna. And what is an advantage of a 5/8 wave whip antenna for VHF and UHF mobile service?
A.
Alpha.
Yeah, it has more gain than a quarter wavelength antenna. And what is the major function of an antenna tuner, also known as an antenna coupler?
A.
It's involved with impedance matching. It matches the antenna system impedance, the feed line and the antenna, to the transceiver's output impedance and makes the transmitter happy. So which of the following RF connector types is most suitable for frequencies above 400 megahertz? I didn't mention this, but think of our friend at AT&T.
B.
Bravo.
Yeah, Mr. Neal, type N. And which of the following is true of PL259 connectors?
B. Bravo.
B. C. Charlie.
C, not B, because they're not watertight, but they are commonly used at HF and VHF. They're the most commonly used. And which of the following is a source of loss in coaxial feed line? Read carefully.
Delta.
Yeah.
Water intrusion for sure. Highest WR increases loss, and multiple connectors in the line will increase loss, so all of those are correct. And what is the electrical difference between RG58 and RG213?
Charlie.
RG213 is the bigger of the cables we saw there, and it has less loss at a given frequency. 25 minutes after the hour, we made it. It is the end of chapter 4. We're going to cut it off here. So happy to have you with us. Are there any comments or questions before we get out of here tonight?
Yeah. Are we going to get into like these antenna coils on their wraps around certain diameters and balance and uns and that kind of thing?
Not in the technician class, but in the general class and in the extra class, we do cover those.
Okay. I need to read up on that.
All right. Ladies and gentlemen, you've been very good tonight. I appreciate you so much, your attention and your interest. Let's go on home. Oh, wait, we are home. Have a great night. We'll be chapter 5 next week. And until then, let me say 73.
Thank you. Thank you, Gary.